Hey there, it's Miss B. In this video, we're looking at the Unit 5, Lesson 5, Practice Problems for Illustrative Math, Algebra 1. So, let's jump in. First here, we have just a question with the table and some stuff like this. So, we have a population, P, of migrating butterflies that satisfies the equation P equals 100,000 times 4 over 5 to the power of W, where W is the number of weeks since they began their migration. So it says complete the table with the population after different numbers of weeks. So let's fill out our table. If we plug in 0, that will give us our initial value. And plugging in 0 here means 0 is going to be in the exponent. So that means that this kind of goes away because anything to the power of 0 is 1. So we just have the 100,000. So we're going to start with that 100,000 in here. Okay. Then when we put it to the power of 1 and multiply this out, if you take 100,000 and you multiply it by 4 over 5, you will get 80,000. And multiplying by 4 over 5 is the same thing as dividing by 5 and multiplying by 4. So that would make 100,000 divided by 5 be 20,000, then times 4, 80,000. But if we apply it to the 80,000, we're going to get different numbers. So applying that to 80,000, if we plugged in 2, we would get 64,000 here. Okay. So then, if we put into the power of 3, we will get 51,200. Okay. And then, if we put into the power of 4, we are going to get 4 is 40,960. So 40960. Okay. So now it says graph the butterfly population. So we're going to try to graph our population, which means if our butterfly population starts at 100,000, we want to actually be able to start at 1,000 and then decrease from there because all of our numbers are smaller than that. So let's see how many rows we actually have here, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means if we started at 10 of these, we could just put 10,000 for each. So I'll make a 100,000 all the way at the top here. You can do your scale a little bit differently if you want. This is just how it worked out, and what I thought would be nice. So if that's 100,000, this would be 10,000 down here. So then 20, 30, 40, this would be 50,000 right here. Okay. And then we want the weeks since the migration began. So we're going to have 0 and then 1 and 2, 3, 4. Now we could keep going to 5 and 6. We don't have specific values for those, but we're just going to plot what we have. Okay. So at 0, we have 100,000. So I'm going to put my starting point here. And then at 1, we have 80. So that would be right there. At 2, we have 64. So there's 50, 64. Let's see. So 60,000 is right here. So we're going to be like right about there-ish. Three weeks is 51,200, so we're just going to be above the 50,000 mark. And then we're going to be at 40,960. So about here. Hold on. Let me actually 50, 40. That just didn't seem right. We do have a curve here. It's just going to be gradual. So I guess, yeah, that is correct. So 40,960 would be there-ish. And we don't have data for the next one, but I'm going to plug it in because I can just keep putting the numbers in my formula. So divide by 5 and then multiply by 4. This would put us at 32,768. 10, 20, 30, 2, something like that. And then if I did this one more time, we'd be at 26. So 10, 20, 6 would put us like about here. So this is actually going to be a curve. It's just a slight one. It's gonna go like this. Okay. Now, if I made my scale a little bit smaller and didn't put 100,000 all the way at the very top, we'd probably see this a little bit differently, but there we go. Okay, what is the vertical intercept of the graph, and what does it tell you about the butterfly population? So that is, if they're asking for the vertical intercept, that's that number, the 100,000. It's our initial value, but we're gonna label it as a point, just because whenever they refer to the vertical intercept, I like to actually give an actual point. So 0 and then 100,000. And we can say there were 100,000 butterflies and this was before migration. We'll say before migration began. That one's a little better. And then question D says, about when does the butterfly population reach 50,000? So looking at our graph, 50,000, we were just above 50,000 after 3 weeks. So we can say it's around there. We can say, because it does say about when, so we are allowed to estimate, round, that sort of thing. We can say around 3 weeks after. Wanted my eraser there, not to just scribble randomly. After migration began. Okay, and that's question 1. For question 2, we're going to move down to this one. The graph shows the amount of chemical in a water sample, and it's decreasing exponentially. So we want to find the coordinates of the points labeled A, B, and C, and then explain our reasoning. So in order to do this, we want to actually figure out what our growth factor is. Now, since this is decay, I'm expecting a growth factor of less than 1. And so if I get something more than 1, I know that I need to go double check what math I'm doing. So if we look just at our graph, so putting our graph center of screen, we can do this using those 2 points. We are going to take this 800. So when we have something at 1 and something at 0, we can take the output value and divide it by the output value before it. So we are going to say And I'll write it over here. I think I have some space to the right. I'm going to say growth factor. And just kind of show that work over here. So I am going to take the 800 and divide it by the 1000. Now, if you know that you can cancel zeros, this can leave us at 8 out of 10, but 8 out of 10 is going to actually simplify and leave us with 4 out of 5. So this is 4/5. Kind of just like the one above it, we're going to use that 4/5. That's not my final answer though, because I need to find the coordinates for A, B, and C. But I also know my initial value was that 1000. So I can actually make an equation here if I really wanted to. Just to help me out. So since I have those two pieces, yeah, I can actually do this whole thing. So I'm going to say that like, we'll just say, what is it, chemical in the water, and we have time and hours. We'll say chemical over time, so like C of T is going to equal the 1000 that we're starting with. It's going to multiply or decrease by 1/5, meaning we're multiplying by 4/5 every hour. So now I'm really looking for A, which is going to be the value at 2 hours, B, which is the value at 3 hours, and C, which is that value, capital C, sorry, I realized I didn't make that C look different than the little c that I'm using for the function, after 4 hours. Okay, so I am going to just plug these numbers into each of these, or you can do this by just multiplying by 4/5 at each go. So I'm going to actually just plug the whole equation in to my calculator. And we'll use 4/5. And this is to the power of 2. Okay, so that says on my calculator, when I plug in 2, I'm getting 640. And then if I plug in a 3, I'm getting 512. And then if I am plugging in a 4, I get 409.6. So 409.6. Okay. So now that I have these, they do actually want the coordinates. So they did say the coordinates of the points labeled. So I am going to actually write these out as coordinates. So we'll say A, and this is 2, 640. B is 3, 512. And C is 4, 409.6. And this is the answer that they're looking for, or that we're looking for, really. So we have to be specific because they asked as coordinates. We have to give them answers as coordinates. So that is going to be it for the first page. Let's flip to the next one. So we have graphs that show the amount of chemical, and we want to state all the statements that are, or select all statements that are true. So this looks like the graph of our previous question, or close to it. So let's figure out what's true here. We have a couple options. The amount of chemical in the water is decreasing exponentially. The amount of chemical in the water is not decreasing exponentially. It is not possible to tell for certain whether or not it's decreasing exponentially. When it's first measured, there were 2,000 milligrams of the chemical in the water. And after 4 hours, there were 100 milligrams of the chemical in the water. So we're just going to select what we know based on what they gave us, because if you look at these graphs, they're definitely different. Our previous one, we started at 1,000, and they did tell us it was decreasing exponentially. This one, they don't tell us, and we have to actually figure out from our graph. So they don't give us any points labeled here. So while it looks like it's exponential, we're actually only going to be able to select one of these first three options, which is that it is decreasing exponentially, it's not decreasing exponentially, or it's not possible to tell. And we're going to select that it's not possible to tell, because while it looks like it, we don't actually have numbers that we can use in order to check our growth factor and make sure that it's the same. It just does look like it's decreasing by a different amount over time, but it's not possible for us to tell. Okay, so let's look at our other pieces here. So we can only select one of those first three. Now let's look at D and E. When it's first measured, there were 2,000 milligrams of chemical in the water sample. So if they're saying 2,000 milligrams, that's talking about this one right here. And yeah, the initial value is at 2,000, so I'm going to select this one. And then it says after 4 hours, there were 100 milligrams. And while it looks like it could be, it's not labeled. So we're still kind of actually unsure of whether or not that's actually at 100. If it lands like on the actual point or on the intersection, then yes, we can say that. But this one we can't say for sure. So we're not going to select it. And that is all for question 3. So just choices C and D. Now that brings us to question 4. This one shows the amount of a chemical in a patient's body at different times, and it's hours since the level was checked. Could the amount be decaying exponentially, and explain how you know? So they do give us numbers, and we are going to check our growth factor. So if we have, we're basically going to work with the 1,000, the 600, and the 360. So what I am checking, so I'm going to write it out over here, what I am checking, I want the 600 over 1,000. That'll tell me the growth factor, or in this case, it's decaying, so it should be less than 1. But the growth factor between 0 and 1 hours. And then I want to know, is that equal to, so when you put a little question mark above it, it means I guess you're checking. I'm not just making that up. That is a mathematical symbol that you may have seen before, but we're going to check if that's the same as hour 2 divided by hour 1. So 360 divided by 600. And so I'm going to plug this in a calculator just to double check. Okay, when we have 600 divided by 1,000, that will simplify out to 3 over 5. And when we have 360 divided by 600, that also simplifies out to 3 over 5. So it does. So while I did that math, I'm going to now give an answer. So I'm going to say yes, the factor for the first now this is the first 2 hours, so we can say So for the first 2 hours, because it just says, is it possible or could it be decaying exponentially? So we'll say, yes, the factor for the first 2 hours is the same. And we're going to mention that we just don't know the rest of the values. So, and we can't, we'll say we can't tell for the rest, but it just looks like it's following the exponential decay model. So we're gonna say, but it looks like it follows that same pattern. Okay. On to question 5. So we have the height of a plant in millimeters is 7. So it's a small little plant at first, but it doubles each week. So we're going to select all expressions that represent the height of the plant after 4 weeks. So this is doubling, which means our growth factor in this case is going to be more than 1. It's growing. So it's actually going to be 2. But we want to look at what actually matches up with our growth factor here. So we want it after 4 weeks. So first off, B is going to be correct because this would be the original 7, and then we'd be multiplying it by 2 every week for 4 weeks. And so this is the format we would use for our exponentials. We wouldn't be adding 4 times 2. That would just be like times 8 or 7 plus 8. And that would be if it was growing by 4 millimeters each week or growing by 2 millimeters for 4 weeks. The other expression that works here is D. This one is multiplying it by 2 every week. And so C and E would not work either. We would not take 7 to the power 4 because that's our initial value. And 7 times 2 times 4 is not going to give us the same thing either. Okay. So moving along, we have question 6. We have the number of people who read a new book is 300 at the beginning of January. And the number of people who read the book doubles each month. So apparently everyone's telling each other about this book and they love it. We're going to complete this table. So it doubles each month, and we have months since January. Now, if this is 0, that means that is January. So in January is 300. Okay, now that's going to double. We're multiplying by 2 here, so this will be 600. And then we'll have 1,200, 2,400, and then 4,800. So what do you notice about the difference in the number of people who have read the book from month to month? We can say the difference, because they're using difference in the mathematical term, meaning if you subtract, right? Like, what is our difference here? So the difference in the first month is 300, from 300 to 600. So we can say the difference is increasing each month. Now it says, what do you notice about the factor, right? So this one, we said this was the difference. And this one is, what do you notice about the factor? In this case, the factor is going to be constant. The factor is the same each month, and the factor is 2. So a lot of times when we say, like, what's the difference? And we're not talking in a mathematical term, but in this case, we are. So for part B, you do need to actually respond to that as if it's a mathematical question. It's increasing as it goes on. Okay, so question D says, or part D of question 6 says, if n people have read the book in 1 month, how many people will have read the book the following month? So this is whatever n is, and then multiplied by 2. So we're going to say this is 2n, or you can write it as n times 2, but I like 2n. That's the standard way of expressing that. Okay, and then that is it for this assignment because we don't have anything below, and I took a peek at the next one, and it's our next assignment. So thanks for joining me on this one. This has been Unit 5, Lesson 5, Practice Problems for Illustrative Math, Algebra 1.